squared. 1/2. What is anything to the 0 power from yesterday's notes? 2, 4, 8, 16. And it asks you to graph that. 0, 1, 1, 2, 2, 4, 3, 8. I'm going to stop there because everything else would go off of the grid I have here. You could keep going.
Okay, equation.
That is the equation.
Oh, that is.
Yeah, that is the equation. So we're going from the equation to the table. What we're going to be working with today is graphing exponential functions. The great thing about it is we have one new thing, and that's the general shape of an exponential function. And then we can use our skills from first semester with transformation, how they move left, right, up, down. All of those things work the same for any function. So that's the first thing we'll look at. Before we do that, this is some general characteristics of an exponential graph. First of all, we need to talk about what exponential function is. An exponential function is one where the exponent is a variable. So up until this point, all the functions we've looked at, the exponent has been, or the variable has been the base. X squared, x cubed. We've looked at a lot of different polynomials. But we haven't looked at any functions where the variable was in the exponent, and that's what an exponential function is. So y equals b to the x, where b is a number and x is the variable. The domain of an exponential function is always negative infinity to infinity. I can raise a number to any power I want to. It may come out strange, but I can do it. I can put any power in that I want to. The range, however, is 0 to infinity, unless it's been reflected or something like that. But if you take a positive number and raise it to an exponent, is there any way to make it a negative number? No, because we know negative exponents just make it really, really small. In fact, there's no way to make it even equal 0. So the range of an exponential function is 0 to infinity. It has a horizontal asymptote at y equals 0. What that means is the graph levels off to y equals 0. It never touches it, but it gets really close to it. And we'll look at that picture again. Some common points on the graph. Doesn't matter what b is, they'll always be there. So a quick 3 points you can plot before you do transformations is -1 and 1 over b. So in our case, ours was 2 to the x. So when we plugged in -1, we got a half. Everyone see what I mean by that? -1 and then the reciprocal of the base. 0, 1, and then 1 in the base. If the graph is going up to the right, it's called an exponential growth graph. If the graph is going down to the right, it's called an exponential decay graph. How many of you have seen an exponential growth or decay graph before? Couple? In geometry? Okay. Exponential growth is probably one of the most real-life applicable functions that you will see in this class. Does anyone know something that grows exponentially? You've probably heard the word before. I didn't hear what you said. Interest, money, grows exponentially. No, linear is straight line growth. Exponential goes fast. How many of you have heard of someone you know getting in trouble with credit card debt? It's because they don't understand this. So this is actually very real world applicable. Exponential growth can make your finances or destroy your finances, depending on which way you make that work in your favor. If you make it work in your favor with exponential growth, where you're getting the interest, then you will make a lot of money. If exponential growth is your credit card debt, then we're in trouble. So we will actually do a finance project later this chapter. See where that applies. Okay, for today we're just going to graph, just do the output part. We'll do the application later. On the bell ringer, we graphed 2 to the x. So keep that graph handy. It looks like this. Question, does this ever drop below the x-axis? If your picture on your paper is dropping below the x-axis, go 6, 6. If your picture is dropping below the x-axis, go 6, 6. It does not drop below the x-axis. See that? Levels off to y equals 0. Okay? Everyone see that? Okay. So, the first thing I'm going to do is 3 times 2 to the x. What does multiplying by 3 do from transformations? Someone who has your note card here.
Oh, yeah. Oh. This is lazy.
If it were negative, stretches it vertically by a factor of 3. What it does is it takes all the y values and multiplies them by 3. Everything else stays the same, but all the y values multiplied by 3. So, let's see what that would look like. So I'm going to make this one a red graph. What's this y value currently? 1. So what would it be if I multiply by 3? What is this one? What would it be if I multiply by 3? This one is. This one is 4. 4 times 3 is 12, so it's actually up here. This one is 1/2. What's 1/2 times 3? 1 1/2. This one is a 4th. What's a 4th times 3? When you are graphing these, I want to see 3 points. I have, 1, 2, 3, 4, 5 on here, but I just need to see 3. 3 accurate points, and I will be happy with that. Those 3 points that we talked about on the last slide would be a great 3 to do transformations. Okay, let's look at the next one. We'll make it blue. What does a negative in front do? Reflects it over the x-axis. So I'm going to take the black graph and reflect it over the x-axis. Is this still familiar? Something we've done before? The only difference is what? Yeah, the graph we start with. We had started with absolute values, we had started with quadratics, we had started with cubics. This time we're starting with an exponential. All the transformations are the same. Again, you don't have to have this many points. The more points you have, the more accurate your graph is. negative with the x. Inside the function.
Reflection across the y-axis.
Reflection across the y-axis. So, earlier I talked about exponential decay. If the exponent is negative, instead of positive, I'm going to get an exponential decay function. Questions about that one? And the last one, no reflections, no multipliers. But what does plus 2 on the inside and minus 3 on the outside do? Down 3 and left 2. Do y'all remember those transformations coming back now that we talked about them? So we're going to move left 2 and down 3. So we're going to take the black graph, pick it up and move it left 2 and down 3. Are y'all okay at this point if we do both of those at the same time? The first time we learned it, we would have only done one at a time. Left 2, down 3. Keep yourself from making a mistake. Because I will count off if you draw below the asymptote. I am going to go ahead and pick up the horizontal asymptote y equals 0, move it down 3, and I'm going to show that with a dotted line. That way I don't accidentally mess up and drop too far down. Does everyone know what I mean by that? So left 2, down 3. It is the same as we have been working with the whole time. You see what I'm talking about? That was the original function. It does matter. It got us those 3 original points, which we're about to talk about because I'm going to do something that's different. Now, the last one was 2 to the x. We started with that on the bell ringer. We plotted 2 to the x by doing a table. I'm going to do the same thing with 3 to the x, except I'm probably not going to draw as many points this time. What 3 points are easy to find on an exponential graph? -1, 1, and 0, right? So before I start, I'm going to graph just the plain 3 to the x, a plain exponential function with that base. That'll give me my 3 points that I want to move around. Again, if you want to plot more points, but you have to have 3. 0, 1. That one's on any exponential graph, isn't it? And then, what happens when I plug 1 into that? 3. Won't it always just be that number? Whatever that number is. So if it's 4, it'll be a 4. If it's 5, it'll be a 5. If it's 6, it'll be a 6. If it's a half, it'll be a half. Whatever that number is, that'll be that base there. And then if I plug in -1, I'll get the reciprocal. I get 1/3. So you have to have those 3 points. If you want to have more points, if you wanted to do 2, 9, you could. You don't have to. Have to see the 3. I like those 3 center points. 3 to the first power. Those 1/3 is that what you're talking about? So this one's always the reciprocal, that one's always the base. And then that one's always 0, 1. So you could just memorize those 3 points and not have to work through them every time. What's my graph do that's different than that one? So what's up 1 and left 2. Up 1 what we would think. So, right, we get that. So I'm going to move up 1. Remember, I want to see you move the horizontal asymptote. That way you don't drop below what you're supposed to not drop below. So move that up. So I'm going to move every point up 1 and left 2. The blue graph is what I want to see on your homework. On your homework, it also will ask for the transformation, so your answer would be up 1 and left 2. Any questions about that one? This is exactly what your homework looks like. So we're going to do a homework problem. Okay, the first thing that I would do before I started graphing is graph the base function. Graph what you called on the transformations homework. What do we call it? The base function then too? So I want to graph the base function, and that's just the function without the minus 2. 1/3 to the x. So if you're in your notes, you might want to write out to the side, to graph 1/3 to the x, plot the 3 points. Right? And what are the 3 points I'm going to plot when I plot 1/3 to the x out? One's a given on exponential functions. It's always there. 0, 1. 1 and the base. Well, in this case, the base is 1/3, right? So 1 1/3. And then what about negative 1? What does negative 1 do to 1/3? The reciprocal, right? So what's the reciprocal of 1/3? It's 3. So let me what we just did there. 1/3 to the x. Now, if you can't do that in your head, what do? Pick up your calculator and do 1/3 to the first power, 1/3 to the 0 power, and 1/3 to the negative 1 power. Your calculator will answer that correctly. But what you'll notice is if you start with a fraction, isn't that kind of the same as a reflection over the y-axis? Well, the reason that is because it's like having a negative exponent. So that's interesting that that's the same. So that's my base function. How has it been moved? Good. Right 2. Does everyone see that right 2? So I'm going to answer that question. That's a horizontal shift, correct? Horizontal shift, right 2. Now on the other one I said, make sure you move the asymptote, right? Does the asymptote move if I move left and right? Does the horizontal? No, because it only moves if I move up and down. So when I expect to see that dotted line is when you move up or down. Is there a shift up or down? No. There's no flux out here. So no vertical shift. Is it reflected over anything? Not from 1/3, right? Now it does look like a reflection at 3 to the x, but there's no negatives anywhere. So it's not a reflection. What is the horizontal asymptote? Or a better question is, did it move? No. So what's the original horizontal asymptote? Y equals 0 is the horizontal asymptote unless it has been moved, which we have seen some that have been moved. If it's moved up 1, then what would the horizontal asymptote be? 1. If it's moved down 1, it would be Negative 1. It's whatever the vertical shift is. What's the domain? Negative infinity to infinity. That should be a give me answer. It's always negative infinity to infinity for any exponential function. The range is not as much of a give me. What do you have to think about when you do range? Okay, if it's been moved, it would change the range, wouldn't it? Let's look. Am I touching? Where's the first place I touched? 0. Do I actually touch 0? How do I say that? Parentheses 0 to infinity. There you go. Very good. So if I have a vertical shift, is that going to change my range? So the range is always going to be either from the horizontal asymptote to infinity or from negative infinity up to the horizontal asymptote if it's reflected. Is this?
The range will do whatever the horizontal asymptote is.
Right. It'll have to do with it. It could be negative infinity to the asymptote, or it could be the asymptote to infinity, depending on if this has a reflection or not. So you will want to look at the graph, but keep in mind that it should have something to do with that asymptote, because that's the place where it's leveling off and not going any lower. Is this function increasing or decreasing? Decreasing. It's going down to the right. And what is the y-intercept? Well, right, and we didn't do that, did we? We didn't draw enough points to know that. So how do you find y-intercepts in general? Put 0 in for x. So easiest way to do this is to just plug 0 in for x. Now if one of those 3 points falls on the y-axis, then just answer the question. But if not, I would go ahead and just plug in 0 for x. If I do that, I get 1/3 to the negative 2 power. What is 1/3 to the negative 2 power? 9. How'd you get 9? It's the reciprocal, right? Because of the negative. And then 3 squared is 9. Of course, you could also use a calculator as well. But the y-intercept is 9. So those are the questions that you're going to be asked on your homework tonight.
So, if they were going to be reflected, what would the credit point be?
There would be a negative either here or up in here. That would cross our reflection. This one is a particularly tough one. Probably as tough as I could make it. It has almost everything happening, doesn't it? I don't care if you answer the questions first and then graph, or if you graph and then answer the questions first. I would probably lean toward graphing first and then answering the questions. I do want you to check it in your calculator, but don't just draw a calculator sketch. I need those 3 accurate points. Do you know what I'm talking about? So I love checking in your calculator, but don't just draw it from your calculator. We want to be more accurate than that. You may remember from transformations this being a particularly tough problem because it has a negative and a +3. Does anyone remember how to deal with that? You do, the negatives reflect. So there is a reflection on this one, actually both x and y. Because I have a negative at both places.
It's the base group, so it would be -5.
5 to the x. Now, if you did -5 to the negative x, that would already have the reflections in it. 5 to the x. Otherwise, it'd be more complicated to graph the first. Okay. So that's my base function. I'm going to graph that really quick. Is that getting quick to graph 5 to the x? What 3 points? 0, 1, negative 1, 1/5, and 1, 5. So that's my original function before it started. I'm going to go ahead and reflect it, both over the x and the y. So start with x. This would stay let's start with y. This would stay the same. This would go over here, and this one would go over here. So that's reflection over x. It doesn't matter what order you do it in, you can do it in either order. And then if I reflect over y, sorry, I said that backwards. This is over y, and I'm going to go over x. So the green graph is the graph after the reflections. Any questions so far? Is there a vertical shift? What is it? Up to. Is there a horizontal shift? And here's the tricky part of this question. There is one. Okay, very good. The 3 causes a horizontal reflection. Now, we need to talk about left or right, and that's where the trick comes in, is the left or right. Normally you would say left because it's plus 3, right? Look back at your note card. How do you find left and right shifting? I think it's called shifting left and right. How do you find that? There's a reason you have note cards. C divided by B, right? And the C is the 3, and the B is the number in front. Most of the time, B's 1. And so you just sort of like, oh, left 3, right 2, whatever it is. What is 3 divided by negative 1? Negative 3. And what would it do if it were negative? It would move it right 3. So the horizontal shift is right 3 because of that negative. So that's a tough one. I haven't done it yet. So we're going to, yes. Or the x and then the y, it doesn't matter which order, you have to do both. No. Okay, so now I'm going to pick the green graph up and move it right 3 and up 2. Again, this is about as hard as I could make it. The first thing I'm going to do is move the horizontal asymptote up 2. That way it kind of gives me a baseline so that I don't get off. So I'm going to pick every point up and move it right 3 and up 2. There was a lot going on in this problem, and you have to do it by hand. However, on a problem this complicated, please pick up your calculator and check your answer. There's a lot of different ways we could have messed it up. If you had accidentally gone left 3 instead of right 3, would you notice when you picked your calculator up? You go, oh, oops, that's over there and not over there. I must have gone the wrong way, right? So you can catch mistakes. You may not be able to answer the question completely, but you can catch mistakes. Horizontal asymptote. Well, what is it? Right, 2. That will always be the vertical shift. And remember, right now we are only looking at the black graph for domain and range. The other ones are. You could even go back on your homework and erase the other ones if they're in your way. What about the range on a block graph? Negative infinity to 2. Is this graph increasing or decreasing? Increasing. It's going up to the right. So increasing. And the y-intercept. I have no idea. So how will I find the y-intercept? Good. Plug 0 in for x. I get 5, and type it in. Negative 5 cubed plus 2. 5 cubed is 125. Then it's negative, so it's negative 125. Negative 123. Does that make sense that this would be negative 123?
Yeah.
It's going down pretty fast. It seems like that could be positive. Put 0 in for x. Okay, any questions? Let me know if you need to borrow one.
I'll have to check first.
Okay, we did examples like numbers 1 through 5. There are only 5 of those, not 100 of them that you have to do. On numbers 11 through 16, let me explain how to do 11 through 16. You not gonna, two more? Two more? Okay, on numbers 11 through 16, you look at the left-hand graph and the right-hand graph and see how it has been moved. So, for example, on number 11, what is the answer on number 11? Right 4. So your answer is right 4, the end. So it's just the left-hand graph to the right-hand graph. Now, there may be multiple transformations if you were going from a normal base graph, but make sure you only go from the left-hand graph to the right-hand graph. That makes sense? So only what's changed from the left-hand one to the right-hand. Okay, that's your homework for tonight. Keep your transformation note card handy.